Today, we're going to talk about the fundamental theorem of calculus. By far, the most important thing you're going to learn today is that the fundamental theorem of calculus establishes a link between antiderivatives and integrals. And after we do that, we're going to look at the geometric significance. It's fundamental for a reason, and in this video, we're going to get to the bottom of all that. There are two parts to the fundamental theorem of calculus. Yes, you are expected to know both these parts. You want to challenge yourself to have a solid grasp over these concepts and not just be able to solve the problems mechanically. That's a huge part of why I'm making this video. Also, seriously, where's my stuff going? Here's the formal statement of the fundamental theorem of calculus, part 1. The derivative of the integral gives you the original back, or in other words, a derivative undoes the integral. To a first-year calc student, this might actually seem pretty obvious. I can assure you it's only because you think an antiderivative and an integral are the same things. An integral is used to give you the area underneath a function. An antiderivative of a function is just the function whose derivative gives you back that original function. We only actually recognized that integrals and antiderivatives were related after the development of the fundamental theorem of calculus. Yes, it is okay to spend a week thinking about this. Before the fundamental theorem of calculus, we knew that if you took the antiderivative, so if you started with 2x, took the antiderivative and got to x squared, and then you took the derivative, you got back to 2x. That's exactly what it means to be an antiderivative. We didn't yet know that the derivative of an integral gave you back the original function as well. In other words, we started to notice that integrals were starting to look a hell of a lot like antiderivatives. Now that we understand why that part is so significant, let's go on to the geometry of the first part of the fundamental theorem of calculus. This part is so satisfying! It's better than getting a Tinder match. Okay, let's recall what d by dx of something means. It means how fast does this thing change when I make x just a little bit bigger. Keeping that in mind, let's go look at the formal statement again. Okay, so if we go back to the statement from the fundamental theorem of calculus, it's saying how fast does this thing change when I make x just a little bit bigger. Now we need to understand what this thing is here. Let's look at this picture here. Let's let this red function be f at t, which means this is the t-axis, not the x-axis. Let's say we want to get the area from a, it looks like a is equal to 5, up until some point x here. If we want the area under a curve, recall that that means the integral from a to x of this function f at t dt. Well, that is exactly the thing that we were looking at in the fundamental theorem of calculus. So we're looking at the rate of change of the area. So when you ask, how fast does this thing change when I make x a little bit bigger? Really what we're saying is, by how much will this blue area grow if we increase x by just a tiny baby bit? Can you see what looks to be the only reasonable answer to this question? If we add on a tiny baby bit to x, can you see how we add on a slice of height f at x to this blue shaded area? If you can see that, then you understand the geometry behind the first part of the fundamental theorem of calculus. Let's do a snap summary. If we look at these two statements, they look like they might be saying the exact same thing, but they're not. This is the whole point of the fundamental theorem of calculus. It's obvious that the derivative of an antiderivative of a function gives you back the original function. It was not obvious that the derivative of an integral of a function gives you back the original function. This established the link between integrals and antiderivatives. The geometric interpretation of this, of the fundamental theorem of calculus, is that if you look at the area here, this blue area will get f at x bigger if we add on the smallest possible slice, because the smallest possible slice we can add on has a height of f at x. Everyone, thank you for watching. Rate and subscribe, and we'll see you next time.